All right, thanks so much for the introduction. Thanks for having me. So the topic here is going to be about incentivizing opt-in, enabling opt-out for text image models. So we're all here because it's a really transformative time for content creation. A whole bunch of different generation backbones, as has just been overviewed, have really left the lab and are serving as the backbones of content creation workflows out in the real world today. Now, this looks like magic, but ultimately models don't come out of thin air. They're really reflections of the underlying training data that was put into them. And that training data ultimately comes from people or contributors. Now, one problem right now is that these contributors are cut off from the models that they're fundamentally enabling. So while we, researchers and founders are excited, there's been a fair amount of pushback. There's ongoing legal battles, there's Hollywood strikes, and digital artists are pushing back, noting that their work is being used without their consent and without compensation. So what can we do about this? So we look at bridging contributors, reconnecting them back to the models that we're creating. And we can look at this from a few different lenses. Okay. One is the idea of attribution. That is, given a generated output from a model, we'd like to trace back the specific elements in the training set that actually made that generation possible. And another is the idea of ablation. We believe that in a lot of circumstances, people should have the right to opt out, and they should have an efficient means of doing that. So we'll first discuss this topic. So a pre-trained model will often have a whole bunch of different concepts, and some of these may be problematic. Some of these include personal concepts or copyrighted content. For example, Grumpy Cat is actually someone's cat that's out there, and they own a copyright over it. There's also artistic styles from living artists that are mimicked within models. And as some of these artists are living, they may not really appreciate that. And then there's the idea of memorized images, where if you have a lot of repeated elements in your training set, the model is likely to memorize and kind of regurgitate that and really not be generating something that's appreciably new. Okay, so what can we do about this? Well, one challenge is that data opt-out and compensation, these are actually just standard practices in content creation platforms, for example, like a stock website. But it's a really difficult concept to implement for generative models because consumers see generated data rather than training data. And training data is, of course, munched together and tangled in the model weights. So if we want to remove something, how could we do that? Well, one naive baseline is to search for all instances within the training set, remove them, and retrain the model. And I can tell you this works, 100% works, but of course, this is going to be very time-consuming and computationally expensive and not really scalable. So can we think of a more efficient way of doing this? Well, one potential solution is to take the training procedure that we had before, that was explained in the previous talk about minimizing denoising loss. Instead of minimizing it, we can maximize it for a given target concept. And let's just go ahead and do that. So if we're trying to wipe away Grumpy Cat, we can tune the model and forget about Grumpy Cat. So that works, it's removed. But the problem is that nearby concepts, for example, this related cat, is also changed, which is undesired. And if you keep doing this, the model is unstable and will completely diverge. So it's not even a stable kind of procedure to run. What we do instead is think about this from a distribution matching perspective. So given a photo of a Grumpy Cat, we'd like to have a stable target for it to run to, which is going to be a superclass that's a nearby superclass. Okay, so you can just think about it as trying to align the distribution of Grumpy Cat towards something more generic like a cat. And we can do some math and formulate this objective. And after we do that, we can both remove the target concept as well as preserve the nearby concept and not affect it. And so we ran this algorithm on a whole bunch of different concepts. For example, copyrighted characters. This is on just one of the earlier stable diffusions. We have R2D2. We can make them into a more generic robot. And then it has this kind of scary looking Nemo, but we can make them look a little more normal. Okay. There's also these memorized images where you have kind of specific identities within the model, and we can try to add some diversity with our method, as well as this video game cover can be diversified as well. And then we have styles of our artist styles. Now, Van Gogh is dead, so he won't object to being in the model, but we could wipe him out with his kind of signature lines here, his signature brushstrokes. And there's also Greg Rukowski, who's a living artist who's became very popular in a lot of these prompts. Additionally, we can target what we'll call problematic composition. So for example, you could have kids and guns in your training set, and in isolation, these concepts are okay. But some model developers may not want to be composing these two concepts together. And by using our technique, you can actually keep the ability to generate kids and guns separately, but remove the ability to generate them in conjunction. And so you can do kind of targeted removal as well that you couldn't do just by cleaning up your trainings. So there is not perfect disentanglement. Okay, so in this section, we talked about removing the concepts within the network in an efficient way by overriding a network with itself. This is a pretty active area. There's been concurrent recent works, and there's ongoing challenges. There's imperfect disentanglement when you remove things, and it's also really difficult to evaluate if something is truly been removed or if it's just kind of hiding there in the network in some other way that you may be able to access later. So this is kind of an active area of research. Okay, so here we discussed ways of enabling people to opt out of model, but ultimately we don't want everyone to be pulling their data and opting out. We want people to be participating in the system, but in kind of a fair and equitable way. And so one way of doing that is to somehow incentivize opting in. And for that, I think a key part of this is solving the problem of what we'll call data attribution. And data attribution is if you look at an output of a generative model, a specific Gen AI image, is the ability to actually look back into the original training set and trace the specific elements of that set that had high influence on making this output possible. Now, this is very difficult because ground truth influence is fundamentally unknown. You have millions or billions of images all munched together through a very long training process. Who knows, at what gradient step did one specific training image maybe, influence this specific output. And so that's the whole name of the game, trying to figure out how to do this in some grounded way. And so my claim is that, or our claim is that you must intervene in the training process in some way to really truly understand the underlying train dynamics when you're ingesting all this training data. And so we had a few attempts at this. So the first I'll call attribution by customization. The starting point is that we don't know which images influence this building. The influencers are unknown, but we can intervene in the training process by customizing the model or tuning it towards one specific exemplar. And by doing that, we can generate a building that we know was influenced by this exemplar image. I won't claim that it's only influenced by this image, but by design, it is definitely heavily influenced by it. And we can use that as a signal to learn attribution from. So we can generate a whole bunch of these images, for example. Take one of these synthesized images, look at the ground truth exemplar as well as other images, could be buildings within the training set. And then we can ask an algorithm, hey, which one of these buildings or which one of these images do you think was the ground truth influencer? Now, of course, we know the answer, and it's the one on the bottom right. And so a good attribution algorithm or a good kind of retrieval algorithm, if you're using that for attribution, would have a feature space that puts the corresponding images together. So you can, using this data set that we've created, evaluate and learn an attribution, a feature space that's suited for attribution. And we can then run that on the base model. So here are some example outputs and images we're retrieving from the 400 million large training set. Okay, here's some more. So you see that even if an image looks like it's so cool and new and creative, a lot of these are actually just kind of recombinations or really heavy reflections of what's already in the training set, which is what you would expect when training a model. Okay. Okay, so here we established ground truth through the customization procedure. There is some limitation in that the pre-training set is ignored. So on this kind of final work, we looked at directly analyzing the training set. What we did here was instead of adding an image in the form of tuning towards an exemplar, we instead tried to remove images from the original training set. And we were very inspired by this idea of a Shapley value, which is a landmark concept in economics, where if you have a bunch of players that are cooperating together, how do you equitably distribute the kind of excess welfare that's kind of created with them acting as a group rather than as individuals. Okay, so as a thought experiment, we thought if you had infinite compute, what would a really good attribution algorithm actually give for you? And so one way of doing that is training on a whole bunch of subsets of that original training set. So the original training set gives you this result. You could train a whole bunch of what we'll call counterfactual models that have every single image either in or out of the training set. Now, this is a lot of models. It's 2 to the n models. But if you were able to get that population of models, you could then analyze them all and see which ones could generate this specific image and which one could not. And that would be reflective of how important the underlying training images were. Now, there's just one problem here, which is that training one model is expensive, and training 2 to the n models is going to be not tractable, obviously. So the whole name of the game here is to create a tractable approximation of this underlying kind of operation. And so what we came up with was what we'll call attribution by unlearning. So you can start with the original model, and you can try to unlearn the synthesized image. That procedure is maximizing loss on the synthesized point while keeping around trying to minimize loss on the original data set, which you can do efficiently through some approximations. After you do that, you can then evaluate which of the training images were damaged. Okay, so our idea here is that we're going to intentionally forget the synthesized example and see which one of the training examples were forgotten by proxy. And the hypothesis being that there's some sort of causal link between those training images that you've identified. Now, to verify this, we can do what's called a counterfactual evaluation, where we can remove the top identified images and retrain a model from scratch without them. And if we've identified the critical training images, removing them should completely destroy the generation. And that can be measured with different types of metrics or objectives. Okay, so this is an expensive evaluation, but we had a brave student, so we went ahead and just did it. We had to do it on modest sizes, which is why these images are not, the latest state-of-the-art Gen AI images. They're kind of on more modest 100K size academic data sets, but we can still kind of gain insight into how effective this algorithm is. And so I'll show an example. Here's a generated image of a bus. Here are different images in the training set identified by our algorithm versus different baselines. You can kind of look at these and squint. I could convince you that maybe our results are better because the generated bus is double-decker, as well as like the orientation of the bus kind of matches better if you take into account flips. But really the ultimate measure is this counterfactual retraining. So we removed the top 500 images which is just 0.4% of the data set. So it's a very small percentage of the data set. And we retrained the method, or retrained the model, and you can see that when we try to regenerate the bus, our method actually is unable to do so because it identified the critical training images, whereas for the baselines, they're pretty much able to regenerate the bus, which indicates that we identified the more critical training images that made this specific bus possible. Okay, here's another example of this skier. So our results, they match a bit better in pose, the number of skiers, etc. But the real test is this counterfactual retraining, where our method ends up destroying the skier much more effectively than the others. Okay, so I can show some more results. And another kind of little kind of plus thing that you can do on top is there's nothing preventing you in the math from doing this on a local level. So instead of running on the whole image, you can actually do local attribution. So for the little stop sign up top, we can find the influential images for that. And for the motorcycle on the bottom, we can find their corresponding influential images. Okay, so we discussed a few different approaches. So one is customization, which adds an image or an exemplar into a model and analyzes its effects. Another is unlearning, or really directly trying to remove content from the pre-trained model and evaluating the results. There's ongoing kind of challenges with this. It's still expensive to evaluate. So in the future, we're looking at more effective approximations. And ultimately, we want something that's both counterfactually predictive and well-grounded, but is also tractable to run and store at scale. So there's still challenges, and this is kind of an open research problem in the setting. So here we're looking at reconnecting creators with models, incentivizing them to opt in, enabling them to opt out. This is kind of top of mind. In the Washington Post, Joseph Gordon-Levitt wrote an article, a year and a half ago about if AI uses your work, it should pay you. And I actually tweeted some of our results at him, and he appreciated that. Okay. So I'll discuss quickly a kind of different topic near and dear to my heart, which is also about enabling creators to have better ownership about what they're generating. And that's at making these systems fundamentally more responsive, controllable, and interactive. And some of my work kind of goes back to past generations. Now this is really a throwback. This is from 2017. I was working on some of the earlier, what we can call Gen AI applications back in grad school. Here I have a grayscale picture of my grandparents, and an interactive colorization system where you can add colored dots and really guide the outputs. Now, this was really fun to play with because it was, the models were so much smaller. They ran in real time. I could just, play with it locally, and I could just tune or kind of really guide the generation towards what I wanted. And so that's sometimes been missing in some of the generative models that we're playing with now. Okay, and this eventually made its way into Photoshop after I joined Adobe. So in earlier generative models, they're called GANs. We looked at adding these capabilities. Back then, a full model would be very slow. It would take 5 seconds after you click it to get a result. And we created something called any-cost GANs, where you could run a small, lightweight network, even on a CPU, and get really fast interaction, get results immediately. Of course, we moved on from GANs to diffusion models. And GANs, they were pretty fast. Diffusion models, because they were running, 1,000 steps of denoising, they were really slow, right? So you'd click and you would have to wait seconds in order to get a result. And so we wanted to help fix that. So we had work on called DMD, distribution matching distillation, where instead of generating an image in 1,000 denoising steps, you could do it in 1 step or 4 steps and really get real-time results back. And this is serving as kind of a backbone of out there in some platforms. And what this fundamentally enables is you to actually interact with the system, which is, I think, what we want. So here's a demo called Turbo Edit, where you upload an image. You can get a long text prompt using captioning systems, and then you can just edit whatever word you want to edit. You can change the straight hair into curly, have her wear a jacket. You can edit the strength of these different words, etc. And you can really be much more in the loop of the creation process, not just click and wait a few seconds and just hope you get something good. Okay, and now, of course, we have video models. If you have played with some of these, they're even slower because a video is much bigger than a photo. So on the left is kind of a Sora-like model. If you click, you're just going to be waiting for minutes on end, at least with the original kind of bidirectional architecture. But on the right here is our method. You can see it's you just click, you wait maybe a second, and you can actually generate a video on a streaming basis. So you could be watching the video as it's actually being generated on the back end. And finally, after generating 15 videos on our end, the bidirectional teacher comes out with one result. So this is a big area that we're working on. This was accepted CVPR recently. Okay, so these are some of the results that we discussed about removing and about concept ablation and about attribution. I'd like to thank my wonderful collaborators here. And also thank you for your attention. My Twitter handles. Thank you.
We'll take 3 questions from the audience.
To what extent with the opting out is there like degradation over time? And is there like collateral damage opt out where, just like a tiny percentage? And over time, if enough people opted out, would it just degrade the model?
Yeah, that's a great question. So, right, when you, ideally you would just be doing like a very surgical targeted procedure but there is going to be damage. So you can remove, one concept, you can remove a few concepts, up to about 10 concepts, and then you start degrading, really degrading the model. But at some point, really, you can afford to retrain it, maybe on like a monthly basis. But on like a daily or hourly basis, you don't want to be retraining the model over and over. So this is kind of a stopgap solution for the actual removal and retraining. Great question.
Thank you, Richard. My name is Olia, company website. I have a question regarding the video data sets. Where do you get them? Do you think that you don't have enough train? How do you arrange and they opt out for the video? Or opt in?
Right. Okay.
Thank you.
Yeah. So that's, I think, dependent on whatever company you're working at, whatever policy they have there. Of course, more data is always going to make your model better, but that's kind of a very, I guess, sensitive legal area and ethical area. So it's, I think, yeah, depending on the decisions your company makes. So I don't know what I can say or not say. So there's probably some public information that I'd be repeating to you. Yeah. Yeah.
Last question.
It's actually two questions, sorry. So one, when you're erasing a concept, do you ever find that like a polysemantic neuron will become monosemantic if you try to erase the polysemantic one? And the second question is, what's your best understanding of why some of these, why there's like a linearity in the latent space? So like there's a smile direction. That maybe this is more true in GANs, and you could just linearly walk across the smile direction, just smiles more.
Mm-hmm. Cool. Okay, the first question, I don't know if we've like specifically analyzed specific neurons in that way. That's a really interesting question. For the second one, yeah, so this idea of kind of having latent space that's nice and well organized was definitely very prevalent in GANs, and you had these nice linear directions. With diffusion models, that wasn't as immediately obvious because you had this high frequency or high resolution noise. But in a more recent paper called Concept Sliders, we actually did find that you could find linear directions as well. In that case, it was in the kind of LoRa space of the models. So I'll point you to that. Yeah, so it's kind of cool to be able to find those directions and manipulate in that way as well.
Thank you. Appreciate it.